So you might have heard people talking about this whole methylation cycle thing and kind of thought, what the hell is this? What's everybody talking about and why is it important to health? You might have also actually had a test done for your genes and actually seen that you do have a SNP in one of the, for example, MTHFR gene. There's a couple of different SNPs you can get. So you might be sort of thinking, okay, well, what does this mean? Do I just take methylated B vitamins? Well, I'm not going to go into detail right now about whether or not you should be taking multivitamins and things like that and whether they should be methylated. I really just wanted to kind of give you a bit of an idea of what this methylation cycle is and why it's important to us overall with our health. So methylation is a process that actually happens in all cells of the body. And so what we're actually doing with methylation is we're putting a CH3 onto different molecules. This is really all it is. It may sound really simple, but it's extremely important. What's a CH3? It's just essentially a carbon and 3 hydrogens. And we will put this molecule onto different other molecules and pass those methyl groups around. And it's essentially a way for our body to be able to metabolize different things that we've created as a way to, for example, get rid of them once we've had enough of them in our body. We don't need them anymore. So it helps with detoxification of things. It helps to activate or inactivate different molecules. So as you can imagine, if this occurs in all cells of the body, it's really, really important. But what are the things that it can impact? So if we look right in the middle of these cogs, we'll see the red cog, which is the folate cycle. And essentially all this is that we're taking in the folic acid from our fortified foods or our supplements, or the folates in our food, and we're just bringing them in and essentially converting them to an active form, which will have a methyl group, as I said, a CH3 attached to it, so that then we can pass that on to different molecules. And you might have heard about this cycle around the whole MTHFR gene SNP that people are now talking a lot about. And while this is a big deal, we do want to understand the MTHFR gene SNP because, as you can imagine, this cog's right in the middle. And so if that MTHFR gene is making you create an enzyme that is either overactive or underactive to a certain degree, it can therefore impact the rest of the methylation cycle. So it's a very important gene SNP to be aware of and perhaps get tested for. But what I think a lot of people do misunderstand with this is that there's like 1, 2, 3, 4, genes that are actually related to enzymes in this little cog cycle. And so when we're getting our genes tested to see if we have any SNPs in the methylation cycle, it's actually really important to go and do the whole thing and to look at all the genes that are related to the whole methylation cycle. Because, if you test one and it's like, okay, that's clear, or even if it isn't clear, there could be a couple of SNPs going on, which can impact different parts of the cycle as well. And as I said, with these cogs, if one of them's moving a little bit slower than the others, then it's going to make them all move slower, and vice versa with it speeding up too. So I obviously put a list of all the different enzymes that are involved in this cycle. And so if you wanted to go and test yourself, it's not cheap, unfortunately, these days, but it is, I think, very illuminating. So if we look at the folate cycle, once we've got that methylated folate, so the active folate in our body, using those enzymes to make it active once we've consumed it, then we're essentially going to pass on that methyl group, and that will go over to the next cog on the right, which is the green methionine cycle. And essentially all we're doing here is handing off that methyl group. And we actually use B12 in this as well. So this is why people will sort of say, if you found that you've got the MTHFR gene SNP, then you will take a methylated B vitamin and you make sure that it has activated B12 as well. And activated B12 essentially just means that B12 has a methyl group attached to it as well. So what we're seeing here is that we have this folate cycle, and that's turning around. It uses B12 that's also methylated, and we're essentially just passing on a methyl group onto the methionine group. And that will then make that cog turn, the green one. What we need to understand as well about this green cog, and that maybe a lot of people don't understand, is you might have heard of homocysteine. So homocysteine, as you can see down there, is part of this cog. And really all we're doing here is, as I said, we're throwing on a methyl group from the activated folate and then therefore B12, and passing it on to an amino acid called methionine. Once that methyl group has been attached to methionine, it will then get passed on to another molecule, which is called SAM. And that is then going to go down a different pathway, which I'll tell you about in a minute. But essentially methionine, the difference between methionine and homocysteine that I'm sure you've heard about is actually just a methyl group. So homocysteine is just essentially where methionine has been demethylated. So essentially we've got methionine and that gets converted into homocysteine. And it's when we've lost our methyl group that methionine becomes homocysteine. And then we go back up, we get the methyl group again, and we become methionine. I hope that makes sense. But essentially that's the only difference. And so often people will look at their, for example, blood work, and we do actually test homocysteine quite a lot these days, because it does give us a pretty good idea as to whether or not there's potential risk for cardiovascular disease if homocysteine is raised. And it might make a little bit more sense to you in a moment why that might be the case and why it's related to other things. But essentially, once we've got that methylated methionine, what we're going to do is then pass on that methyl group to another substrate, which is SAMe. And I'm sure you've heard about that too. But SAM is one that is going to then be used in producing, methylating other things. So methylating, for example, neurotransmitters or methylating hormones and things like that to help them to be metabolized and eliminated. And as I said, once we lose that methyl group, we then get homocysteine. And then homocysteine can then again be converted back to methionine once you have that methyl group again coming from the folate. So as you can see, it's a cycle. Things are just going round and round and round and round and round. But of course, if something in there isn't working properly, like let's say you're not able to get that methyl group from the folate because you haven't got enough folate in your diet, or your body is not able to methylate it, like for example, you have a SNP in one of the genes associated with converting the folate from our diet to the methylated form, the active form, then you can imagine there would be a bottleneck. And often when we have this issue occurring, we see homocysteine rising. And that's just because it's like trying to go back to be converted to methionine, but it can't because there's no methyl group to be able to convert it to methionine. So it stays as homocysteine and it just builds up. So the next cycle that is very important to talk about here, and probably my favorite part of this, is the transsulfuration pathway. So if you look down under homocysteine, you'll see this triangle, this orange triangle, and that is the transsulfuration pathway. So the purpose of this pathway is to make something in our body called glutathione, which I'm hoping you've heard of before. It's becoming well acknowledged now by most people, and it is essentially our body's master antioxidant. So it's the way that our body will be able to deal with free radical damage, and we're able to then convert those free radicals to innate substances like water. And so this is why we need glutathione. It's very important for dealing with our oxidative stress. And so in this cycle, what we're going to do is we're going to take homocysteine. And so once we've created in that methylation cycle that homocysteine, we can then, if we need to, and I really want to reiterate here, this is all dependent on whether our body needs that glutathione at that point or not. If our body doesn't have a huge need for that glutathione, we don't have a whole lot of oxidative stress going on, then we'll just continue going through that methylation cycle. We'll just keep converting that homocysteine to methionine and then into SAM. But if we do have a high oxidative demand and our body's going through some inflammation, for example, then we're going to need more of that glutathione pathway. And so instead of making methionine, that homocysteine is going to be converted down into the transsulfuration pathway. And there's an important gene again involved in this. It's called the CBS gene, and allows us to make glutathione from homocysteine. There's a couple of different steps in this as well in this pathway. And this is where you may have heard of an amino acid called cysteine. And essentially we're going to convert that homocysteine down into something called cystathionine and then to cysteine, and then that cysteine can get converted to glutathione. So this is where you might have heard people say, oh, if you've got low glutathione levels or you're going through a lot of oxidative stress, you can take a couple of supplements. You could take cysteine on its own, which is an amino acid, or you can take N-acetylcysteine. And as I'm sure you can see in this picture, it makes sense that if we give more of the substrate needed to make glutathione, then hopefully we're going to have more glutathione in the body. But there's a big point I want to make here with the transsulfuration pathway. As I said, we will only push through the transsulfuration pathway down into glutathione production if we actually need to, if our body's in a lot of oxidative stress. I mean, you'll always be going down it a little bit anyway because we're always exposed to oxidative stress. But if your body is going through a huge amount of oxidative stress, let's say you're sick, or you're exposed chronically to a chemical or something that your body is trying to deal with, you're going to push down the transsulfuration pathway more so that you can create as much glutathione as your body needs. But as I said, in order to do this, we need to take that homocysteine and push it down into the transsulfuration pathway to make glutathione. But of course, that leaves less homocysteine to be converted back into methionine once we have those methyl groups being supplied to it. So what I'm trying to say here is that if you have a lot of oxidative stress going on, then it makes sense that you are going to be going through the production of methionine less. So while you might not be building up heaps of homocysteine, it is quite important to think about this in a way of, all the things that we require from creating methionine, and one of them being SAMe, which then will go into making, for example, neurotransmitters, helping us to metabolize them, helping us to metabolize our sex hormones like estrogen. It's important to understand that all of this is going to reduce if we are pushing down too much through the transsulfuration pathway. I hope that makes sense. So essentially, if we need more detoxification happening, then we are going to be reducing our methionine, and we're going to be going through that recycling process less. So while we're on neurotransmitters, I think we should move up to the left-hand side top, which is the biopterin cog. And you'll see it's a darkish orange here. And this one's really important when it comes to mood. And that's because we essentially are utilizing that folate. And again, this is why folate being activated in the body is so important for everything. It's right in the middle there. And we take that active folate and we use it to convert BH3 to BH4. And BH4 is really important to help to produce our neurotransmitters. So think serotonin, think dopamine, think adrenaline and noradrenaline. And I'm sure you already know that if we are low in things like serotonin or dopamine, we could end up with really low mood, depression. We could even end up with gut-related problems if we're not producing enough serotonin, things like that. So if you have issues with mood, it's important to figure out if this system is working properly. And once again, as I said, this is where active folate is so important, because we require that active folate to be able to produce our biopterin and therefore be able to produce our neurotransmitters. And so essentially what we're going to be doing here is we're going to be taking that biopterin. It's going to help us to convert our precursors, which are, for example, our tryptophan, and we're going to be able to convert that tryptophan to serotonin. And as I'm sure most of you know, we then can convert that serotonin to our melatonin. So therefore it's involved in sleep as well. We can take our tyrosine or our phenylalanine, convert it to tyrosine, and then convert it to dopamine. And then dopamine can also get converted to our adrenaline and noradrenaline as well. So as you can imagine, if we don't have, number one, enough folate coming into the system that's activated, we're not going to be able to do this. If we aren't able to provide enough of our substrates like our tryptophan or our tyrosine, then of course the neurotransmitters aren't going to be able to be produced either. One thing I think is also important to reiterate here too is that every single one of these steps involved in all these cycles requires these enzymes working properly. And each of these enzymes require cofactors. What are cofactors? They're nutrients. And so each requires different sort of nutrients in order to actually make these enzymes work. So if you can imagine, let's say you're deficient in something like B6, which in this particular cycle is very important, B6, then that enzyme doesn't work. You can't convert the substrate into the product, and this might mean that you have low levels of, for example, serotonin, dopamine, adrenaline, noradrenaline. I hope that makes sense. But one other thing that's really important with this cycle is it's very heavily related to the nitric oxide cycle. And this one is of particular interest to me because I have Raynaud's disease, and so I'm trying to figure out where that's coming from. And my thoughts are that there's something possibly going wrong with a gene SNP involved in this pathway where I'm not able to produce, say, enough nitric oxide. Why do we care about nitric oxide? It's involved in the dilation of our blood vessels. So this is where, again, this whole methylation cycle can be a big problem if there's things not going right with it, and heart disease. So if we're not able to make nitric oxide, we're not able to dilate our blood vessels very easily. And of course, we're not able to then get nutrients to our cells in our periphery. And this is where people like myself in the wintertime, if we're not getting on top of our Raynaud's disease. We don't get the circulation to our fingertips and our toes, to the periphery, and essentially that tissue dies off. And I've actually experienced that myself. It's really awful. You get little black spots all over your toes and things. So hence why I'm very interested in trying to figure out what's going on there. So as you can imagine, nitric oxide is very important, and this is where you might see issues of anything where you need to get nutrients and blood to parts of the body. So this would affect basically every cell of the body, and this is where you'd see issues for people in like erectile dysfunction or Raynaud's disease, or not getting enough blood to the parts of the brain, or tissue necrosis, things like that. And of course this can affect our heart health as well. And then next to this nitric oxide cycle as well is our Krebs cycle, and you may have heard of that. That's our energy cycle, and so this helps to turn the nitric oxide cycle and vice versa. And so as you can imagine, if there's issues going on with these enzymes, then of course our energy creating capacity isn't going to be working properly. We're not going to be able to make energy from the food substrates that we eat. So I hope all this makes sense. It's very in-depth, as you can see, and I'm sorry this video has become a really long one. I really try to make them as short as I can. But I just want to reiterate something here as well, and I'm going to show you a picture here to make this hopefully clear. And this is a fantastic picture from Genova Diagnostics. I think their pictures are just so clear. What you can see here, now don't worry too much about the details here, but all the little blue boxes here are enzymes. And so you can see little crosses next to some of the enzymes. This is just an example of where you can have gene SNPs. So for example, if you see the MTHFR gene involved in the folate cycle down the bottom there, this particular person has 2 crosses next to the MTHFR gene. Now, I don't know which gene that specifically is. There's 2 with the MTHFR, but it means that one of their genes is homozygous, is a homozygous SNP, which essentially means that that gene is going to produce an enzyme that is in some way changed. So it might mean that the enzyme, for example, doesn't work as quickly, and they're going to have a bit of a problem here. What you might also notice too is that, next to some of these are you might have a ZN, which means that zinc is involved in this enzyme working properly. You might have a B6, that means that B6 is involved in making that enzyme work. All of these enzymes require different cofactors to make them work properly. So it's really important when somebody's dealing with any symptoms related to methylation problems. So let's just quickly say what they might be: neurotransmitter problems, mood problems, weight issues, issues with too much inflammation. It might be issues with circulation. It might be sleep problems. It might be depression. It might be headaches. Basically, anything could be related to the methylation cycle. It's important first to, before we do anything else, figure out, do we have any deficiencies in our vitamins and minerals? Because as you can imagine, you might actually not have a SNP in a gene related to these cycles. You might just have an enzyme that's not able to do its job properly because it's missing cofactor nutrients. So if you're able to supply the body with all the cofactors, then perhaps that issue might end up resolving on its own just by supplying all the vitamins and minerals. And this is why I think a multi-pack, multivitamin can be really useful to figure out where we're going here. But it can also be useful to test your genes. And if you have the funds to be able to do that, it's a really, really illuminating thing to do, because you could see little SNPs that you might have in these genes. And what does that mean? It doesn't mean that you can't do the jobs. It just means that there might be a reduced capacity for that enzyme to work, for example. So what you could perhaps do is increase the availability of the cofactors that are involved in that particular step or that particular enzyme. That might help to just push it through a little bit further. I think that's a really nice way actually of doing it. But like if you see that that you have a lower capacity, for example, to make glutathione, then perhaps providing the body with some exogenous glutathione can help. I hope that's a good example. If you have any questions on this, please let me know. I can go into further details in different parts of the cycle if you're interested or if you're having problems. But once again, I'm sorry for making it so long. If you're still with me, heads up to you.